Hello. Let's talk a little bit about level 2A, which is going to be some slightly more complicated force diagrams. Let's talk about this diagram of this box right here. We've got a box that's on the ground. It's not moving. So the forces on this box must be balanced, right? So we know the forces are balanced. And you might be like, okay, this is an easy problem, right? What two forces are acting on the box? Well, we've got gravity down or weight down, right? Weight or the force of gravity, same thing. And then pointing up is the normal force, right? And they're equal and they're opposite. So if we make the force diagram for that, it'll be very easy. We've got our normal force going up. We've got our gravitational force. I messed that up. Sorry. We've got a gravitational force going down. So Fg, which we can also call W, right? Same thing. And we've got Fn, and they're the same size, right? So they're balanced. It cancels out. So if you guys are thinking, okay, math brain time, your math brain might be saying, okay, we mark these as the same, right? That way we know these arrows are of the same length. Okay, great. Everything's lovely. They both are on the same axis, the y axis, right? So if we've got y vertical and we've got x horizontal, like now we know that's our plane that we're working on. That's our two-dimensional plane we're working on, right? Now, that's easy. What happens if we have a box like this that's laying on an incline, right? And it might be on a this might be a 90-degree angle in the triangular incline that we're on, but we've got this box, right? It's sitting here. Well, we know for sure the following information. We know that gravity or weight, right, the gravitational force on an object is always pulling objects straight down. We also know that normal force needs to be pushing objects off of the surface at a 90-degree angle to the surface. So we know those two forces are there, right? So that's great, but we also know this object isn't moving, right? Because I didn't animate any arrows or anything into it. So this object is not moving, which means the forces still need to be balanced. Are these forces balanced? Well, are they even pointing in the same direction or the opposite of each other? They're not, right? That's a problem. So we have a bit of a conundrum here, right? And the problem is this, right? We have this downward arrow and we've got this diagonally up into the left arrow, which is an issue for us. Now, we also have to think about, okay, how are we going to organize this based on our X and our Y plane? Because right now we've got a Y direction and then we've got a somewhere in between both of them direction, which is troubling. So how are we going to figure out if these components can work together or what happens here, right? So let me get another color. We'll go with green. So let's label this. I know we didn't make a free body diagram here, but I wanted to be super clear about what forces we're acting in what direction. Okay, so let's take our normal force here, right, or our gravity force, right. So you could actually break these forces up into pieces. Now, here's the thing: if the object is moving, it's not going to be bouncing off of the hill. It's not going to be going through the hill, right? So it's probably going to be moving along this path, right? Right? So if the box were to be moving, it'd be moving along this path, right? So if you take this path and then you look at the other arrows that are on here, which ones can you make into a coordinate plane? So what if we take our x's and our y's? What if we make our y direction this way? If we make our x direction this way, right? So we just take our coordinate plane and we just tilt it 45 degrees or whatever to the left, right? So now y direction is up and down, and our x direction is across, right? So then this would be our other x direction going forward or whatever, right? So this is going to allow our box to move on one of these coordinate plane directions, on one of these axes, which is what we want. And we want it to move on the x, right? So we're just going to tilt our axes a little bit, and we're going to look at that way. So now that we've tilted the axes, now you need to say, like, okay, what stuff actually fits this axis and what doesn't? So our F in, our normal force, is right on the y axis, which is great. We don't have any forces currently that are moving left to right, but we're going to in a second. Now, the next problem is, okay, take a look at our gravity force. Well, it breaks the rule, right? It doesn't have just it's not just on the x or the y axis, but we want it to be able to be, right? So what we can do with it, and I'm going to erase this 90-degree angle here just for the sake of making the problem easier, is we can break it into a triangle, a right triangle, like this. Now we can say, okay, this is an FG in the y coordinate direction, right? And then this piece is an FG in the x coordinate direction, right? And we now know that FGY squared plus FGX squared equals FG, right? Because A squared plus B squared equals C squared. You see how I made this a 90-degree angle? Now, this isn't exactly how you're going to do it in high school physics, but it's good enough for our explanation now, okay? So now we know we've broken this longer piece into two components. It has a Y component and an X component. Now, here's what we know must be true, okay? We know the following information must be true. FG in the Y must be equal to F in, right? Because if they were not equal to each other, then the box would be shooting off of the ramp, or it'd be getting smashed into the ramp, which it's not doing either of those things. So this must be a true statement. Okay. Now, if we know that the force is overall, the net force, right? If we know, hello, if the forces are balanced, the F net needs to equal to 0 newtons, right? As of right now, if we cancel out our F in with our FGY, we know that we still have FGX that's pulling our box down the hill. So the box would be moving down the hill unless there's another force on the box. And you're probably all thinking this. Okay, we have to have another force that's going up the hill, right? There's our uphill force. And what's it doing? It's trying to keep the box from going down the hill. So what is it? It's the force of friction, my friends. Okay, so now we know we have another statement that's true, and it's that Fgx has to be equal to the force of friction. Okay, now that's actually the main reason that we tilted the axes, because we had two forces that were in line with them perfectly, right? Friction going up the x-axis and normal force going up the y-axis, and then we had one force, gravity, that wasn't compliant with this situation, right? So this would have been our Fg right through here, right? So we then broke it down into two pieces, a y component, right, that goes to here, and an x component that goes to here, right? So we broke those pieces apart, broke it into those two pieces. And that's what helped us to kind of solve this problem. So now we know, okay, this is a true statement. The forces must be balanced. These forces must be balanced as well. So everything's good. Everything's happy. We're great. Everything's lovely. Now, let me show you another situation, okay? I know it's going to be kind of a long video, but I want to make sure that you see this very clearly, because once you see it a couple times, it's quite easy. Okay, so now we've got a box, and it's going to be laying inside of, so we'll dash this off to indicate that it's a wall, and we'll dash this off to indicate that it's a wall. It's laying inside of this kind of V-shaped border, right? So let's take this box and draw its free body diagram, shall we? We know for sure, right, that if this is, hello? We know for sure that if this is the box, we have to have the following: gravity straight down, right? We also know that for every surface it's in contact with, it must have a 90-degree normal force coming out of it, right? So we also know that there is a normal force here, and there's a normal force here, huh? We know that has to be true, right? Okay, now we also know this object's not moving, so the forces must be balanced. Make that look like an actual B. So we know that the F net must equal 0 newtons, right? So we know that the vertical component that we're missing, that would go down the middle here, boop, 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 for both of these FNs has to be equal to FG, right? So we'll call this one FN1 and we'll call this one FN2. Okay. So we know that the Y components of each of those must be equal to gravity, right? And that the X components are going to cancel each other out. So if we look at FN1 right here, we know that it is an arrow of this size, and we know that it must, let's use a different color. We know that it must have a Y component. Actually, let's just do that. And we know that it must have an X component, right? Okay. See what I'm saying here? So we've now got in red F in 1 in the X, and in green, we've got F in 1 in the Y, right? Similarly, we'll have the same thing for F in 2. F in 2 is this guy, right? F in 2. He's also going to have an X and a Y component. So let's put the Y in, yoink, and then let's put the X in. Sorry, that's a little sloppy, my fault. So now we know we have F in 2 in the X, right? And we switch back to green, and we have F in 2 in the Y, right? Now, what we need to know here is, or what we do know here is, F in 1Y plus F in 2Y must be equal to Fg, our weight, right? That has to be true. We also know this is true. F in 1x has to be equal to F in 2x, right? That was supposed to be in red. Sorry, I don't know why I didn't change colors. I did click it. Oh well. So we know that's true, and we know that's true. If these are both true statements, then the forces are balanced, right? And everything's good. Now it's hard to indicate that with these arrows, right? So I probably either need to make my force of gravity arrow look a little bit smaller, like this, right? So that kind of looks like that kind of makes sense. If you were to stack these two arrows on top, they might make this arrow as a whole, right? Then they would cancel out. But I just wanted you to see kind of how that problem works. Similar thing is true with tension if you're hanging from multiple ropes or stuff like that. So just think about, do you need to shift the axis? In this case, we didn't have to, because the vertical axis was the easiest one to deal with. But you can always shift your axes. Try and make sure you can figure out how to balance your forces. Okay. That's the intro, and it's incredibly long. I'm really sorry. Hopefully these examples help you with the work that you're about to do. If you have questions, keep referring back to the video. If you have more questions, just ask. Please use your feedback and tracking sheet. Thank you.